Hi, the next topic is coefficient of determination, R square. So R square describes the overall fit of the model. So here's the definition of R square. So R square is defined by 1 minus residual sum of square over total sum of square. The residual sum of square is defined by this quantity. So yi hat, yj hat is the fitted value of the regression. So we see basically the residual, squared residual, the sum of squared residuals here. And denominator is yj minus y bar. So y bar is an estimate for yj if we don't have any predictors. So if the regression explains the most variability in y, so this R square approaches to 1 because the numerator of this term, it gets smaller. And if this regression model almost doesn't explain anything, then this y hat and y bar are almost the same value. So this approaches to 0, entire quantity approaches to 0. Yes, so we can say that this R square is the proportion of variance of y explained by the linear model. So this is a measure for overall fit of the model, and R square is always between 0 and 1. And we cannot say what level of R square is high or what level of R square is low. For example, if you can predict the stock market's daily return by your morning blood pressure, and if R square is 0.1 maybe, still it's extremely high if your blood pressure can explain the stock market movement. But if y is the size of the left hand of people and x is the size of the right hand of the same people, x and y are very closely related. So even R square of 0.9 is very low. So whether or not R square is high really depends on the context. So next definition, so adjusted R square. This is slightly different version of R square. So adjusted R square is defined by this formula, 1 minus RSS over n minus p. Here, p is the number of parameters in the linear model, over TSS over n minus 1. So the idea is that if we have more predictors, then RSS is naturally smaller than TSS. Even if all predictors are not really meaningful, if we have finite data set, for example, 100 observations, and we have 20 parameters, 20 variables to explain, it's likely that just by chance, some linear combination of 20 variables explain the sum of the movement in X, relationship between Y and X. So we penalize this term by dividing smaller number. So RSS is naturally smaller. So we divide RSS by smaller number and TSS by relatively larger number. So to be more precise, if this linear model isn't useful at all, expectation of this adjusted R square is equal to 0. So this is kind of the fair version of R square, and often in applied statistics, the adjusted R square is used. Oh, here, why we say R square. Actually, R square is the same as correlation coefficient square. So if correlation coefficient is 0.9, R square is 0.81. Okay, so now our examples. So L mod is linear model we defined. And to extract R squared, you can type summary of L mod. So this is one object. Then within this object, we have a kind of sub-object R dot squared. And $sign R dot squared get this 0.05388. And adjusted R squared, if you wanna obtain this, $sign adjust adj dot R dot squared. Of course, you can do everything from scratch. So if you defined RSS, or actually the order is not really correct, but we have already defined RSS. Then we define the TSS. Then we can get 1 minus RSS over TSS. Then we get the R squared. So RSS, I didn't mention, but the RSS is sum of residual of L mod square, then 1 minus RSS minus TSS is R square. To get adjusted R square, you can get this by dividing degrees of freedom. So here degrees of freedom is n minus 1, here n minus p. So we get the same number as this. Okay, so we discussed the R square and adjusted R square. So R square and adjusted R square represents the overall fit of a linear model.